Welcome to Learning with Philemon. In this video, we will be looking at molecules in which there are 6 electron domains around the central atom. For an introduction to valence shell electron pair repulsion theory, VSEPR, please see the video VSEPR. Sulfur hexafluoride, SF6, has the following structure. Sulfur has 6 valence electrons. It uses all these to form 6 single bonds with fluorine atoms. Note that fluorine atoms have 7 valence electrons and require only one single bond to complete their octet. As sulfur uses its 6 valence electrons, it has no lone pairs of electrons left. There are 6 electron domains around sulfur. All of them are bonding pairs. Note that sulfur has 12 valence electrons after bonding. This is called an expanded octet, when an atom has more than 8 valence electrons after bonding. Elements in period 3 and above are able to have expanded octets as the electrons can occupy their d orbitals. The molecular geometry is octahedral. These 4 fluorine atoms are in the same plane. The dashed bond indicates that the atoms are going into the page away from you, and the bold bonds indicate that the atoms are going out of the page toward you. The bonds arrange themselves as far apart as possible in this plane so as to minimize repulsion, so the bond angle is 90 degrees. There are 2 more fluorine atoms on the vertical axis that are perpendicular 90 degrees to this plane. On chemtube3d.com, see the link in the description, you can visualize this 3-dimensional structure. Rotating the molecule so that the fluorine atom on the vertical axis is in the center, we can see the 4 fluorine atoms in the same plane. The bond angles are 90 degrees. Rotating the molecule so that the 2 fluorine atoms on the axis are vertical, we can see that the bond angles here are also 90 degrees. Chlorine pentafluoride, ClF5, has the following structure. Chlorine has 7 valence electrons. It uses 5 of these to form 5 single bonds with fluorine atoms, leaving 1 lone pair of electrons that remains on the chlorine atom. To draw correct Lewis diagrams, remember to always count the valence electrons in the central atom so that you do not forget any remaining lone pairs. Note that chlorine now has an expanded octet with 12 valence electrons. There are 6 electron domains around chlorine. As there are 5 bonding pairs and 1 lone pair, the molecular geometry is square pyramidal. This is similar to the octahedral geometry, but the bond angles are a bit lower. This is because the lone pair of electrons repels the bonding pairs, making them move closer together. Xenon tetrafluoride, XeF4, has the following structure. Xenon, like the other noble gases, has a complete outer shell, so it is unreactive. However, it can form some compounds. Xenon has 8 valence electrons. It uses 4 of these to form 4 single bonds with fluorine atoms, leaving 2 lone pairs of electrons. Note that xenon now has 12 valence electrons after bonding, an expanded octet. There are 6 electron domains around xenon. As there are 4 bonding pairs and 2 lone pairs, the molecular geometry is called square planar. This is similar to the octahedral geometry, but there are lone pairs of electrons on the vertical axis instead of bonding pairs. As the repulsion from both lone pairs is equal, the bond angle remains at 90 degrees. Remember that all these 4 fluorine atoms are in the same plane. The trifluoroxenate II anion, XeF3-, has the following structure. Note that this compound has only been detected in the gas phase. There are no other examples of this molecular geometry, so you will most likely not be asked to draw this. Xenon normally has 8 valence electrons, but the anion has a 1- charge, so xenon gains an electron. It uses 3 of these valence electrons to form 3 single bonds with fluorine atoms, leaving 3 lone pairs of electrons. There are 6 electron domains around xenon. As there are 3 bonding pairs and 3 lone pairs, the molecular geometry is called T-shape. Check out the previous video to see the T-shape molecular geometry with 5 electron domains. This T-shaped geometry is similar to the octahedral geometry, but there are 3 lone pairs of electrons. The repulsion from the lone pairs of electrons decreases the bond angles to less than 90 degrees. Note that the geometry is called T-shape because the 3 atoms form a T. There are no molecules with a linear geometry with 6 electron domains. However, the following ion, XeF22-, could have such a geometry. With the 2 extra electrons gained, xenon could form 2 single bonds with fluorine atoms and have 4 lone pairs of electrons. In this geometry, you would have the 4 lone pairs of electrons in the same plane. The 2 fluorine atoms would be on the vertical axis, perpendicular to this plane. The bonding pairs arrange themselves as far apart as possible at 180 degrees. In this table, we can see that there are 3 structures that are called linear, with 2, 5, or 6 electron domains. There are also 2 structures that are called T-shape, one with 5 and one with 6 electron domains. As discussed before, it is unlikely to get asked to draw T-shape or linear geometries with 6 electron domains, as few or no such compounds exist. Remember that all molecules with 6 electron domains around the central atom, seen in this row, would have the same electron geometry. They all have an octahedral electron geometry. However, depending on the number of bonding and lone pairs of electrons, the molecular geometries differ from octahedral, square pyramidal, square planar, T-shape, or linear. As discussed, all 5 shapes have a very similar 3-dimensional structure. To consolidate your learning, I would suggest you attempt to draw different compounds, build them using Molymods, or view them using the chemtube3d.com website. Thank you for listening. If you haven't already, please subscribe for more content. Stay curious.